Hi everybody. Today we're going to continue learning about gases, and today we're actually going to learn your first gas law. And a gas law is something that says the relationship between two different variables, usually. So in this case, today's gas law we're going to learn about relates pressure and volume. And hopefully you remember from the last video what pressure is, what some of the different units of pressure are, and how we can convert between the different units of pressure. But remember, we get pressure when gas particles, whether they're atoms or molecules, run into their container. And every time they run into the sides of their container, they exert a tiny little force. But when we add up all of those forces, that adds up to a pressure. And today we're going to learn the relationship between pressure and volume. And you might have done a quick little experiment on this and kind of found out the relationship on your own. So this relationship is known as Boyle's law. And Robert Boyle came up with this in 1662. So it's been around for a couple centuries at least. And Boyle said the volume of a fixed amount of gas at constant temperature is inversely proportional to the pressure of that gas. The volume is inversely proportional to pressure. So what does this word inversely mean? That means as one goes up, the other goes down by the same proportion. So if one goes up by 3, the other must go down by 3. If one goes down by a factor of 2, then the other goes up by a factor of 2. So how did Boyle figure this out? Well, kind of the same way that you figured it out in your activity. So he noticed that when he took a certain amount of gas and trapped it, so that's what this word fixed amount means. So we have to have the amount of gas has to be constant. We have to have the same mass of gas, or you could even say we have to have the same moles of gas. But when we keep that amount of gas and we trap it, and we compress it or we expand it, we can see what happens to the pressure or volume. And you might have noticed from your lab that whenever you take the pressure and multiply it by the volume, you're getting a constant number. That only works though, of course, if it's the same amount of gas, and actually it only works if the temperature stays the same. But when you did that lab, your temperature probably stayed the same. And instead of writing out the word constant, we can use the letter K. So the pressure times the volume always gives us the same number. But if the pressure and volume always give us the same number, doesn't that mean that some other pressure and volume at some other point in time must also be equal to that number? As long as I didn't change the amount of gas, as long as I didn't change the temperature, then it seems like multiplying the pressure and the volume at one point in time should give me the same number as when I multiply the pressure and volume at another point in time. And the way we normally write Boyle's law is by setting the pressure and volume at one point in time actually equal to the pressure and volume at another point in time. So that would be P1 times V1 equals P2 times V2. This is really convenient because if we know the pressure and volume that we start with, we can easily find the volume at some other pressure that we want to know about. Or if we know the pressure and volume when we start with, we can easily find the other volume if we know what pressure we want it to be in. So this is how we normally write Boyle's law, but we could have written it a little simpler, and that was, like I said, just P times V equals K. So what if we were to graph that? What if we made a graph of volume versus pressure? So we need a graph that as one goes up, the other goes down. So as we get a higher number on one axis, we need that to be a smaller number on the other axis. And you might remember from math class, this is what that graph would look like. This is an inverse function. We can see as the pressure goes up, the volume is going down, and we're getting a smaller number here. and vice versa. So this is what a pressure versus volume graph looks like. It's not a straight line, it's actually kind of a curve. So let's try a quick question. When the volume is cut in half, what should the pressure do? So go ahead and pause the video and see if you can get this right. When the volume goes down by 2, what should the pressure do? And we can actually find this on the graph. So here's our first point in time. We could say that that volume is maybe 2 liters. We'll keep it simple. So the question is asking, what happens when the what happens when the volume gets cut from 2 liters to 1 liter? Wouldn't that be the data point for 1 liter over there? And you can easily see what happened to the pressure. When the volume went down by 2, the pressure went from here to here. That looks like about double. And this is Boyle's law. When volume goes up, pressure goes down by the same factor, or vice versa. So actually the correct answer here is doubles. Boyle's law says when the volume goes down by 2, the pressure should double. Well, there's two different reasons for that. The first reason is our graph. We can find the points on a graph. We can see how they relate to each other. But the other reason is P1 V1 equals P2 V2, Boyle's law. We could even do the simpler version of that. P times V equals K. And if the volume goes down by 2, but this has to still equal the same number, because remember K means constant. So if we divide the volume by 2, but we still have to make that equal the same number, the only way that's possible is if the pressure goes up by the same factor. So there's actually two different ways to explain this. Let's try a problem. The problem we're going to try is this one. If a balloon filled with helium has a volume of 1 liter at 1 atm, what will the volume be at 790 millimeters of mercury? So what some people like to do is go through and figure out what the variables are. So 1 liter is that pressure or volume or temperature? Well, liters are volume, and 1 atm sounds like a unit of pressure. And we know that these two numbers go with each other because we know that the volume of the balloon was 1 liter when it was 1 atm. So let's actually call this V1 and P1. And it's asking what will the volume be? So which variable do you think it's asking for? V2. What will the volume be at 790 millimeters mercury? You might remember from the last video that millimeters mercury is a unit of pressure. So it seems to me like we have a V1, a P1, and a P2, and we need to know the V2. And the good news is we have a law for that. It's Boyle's law. P1 times V1 equals P2 times V2. Okay, so the first thing we're going to need to do now that we've sorted out which variables we have V1 and P1, and we have P2, but the question is asking for what will the volume be, so we need to know V2. So the first thing we need to do is double check and make sure all of our pressures and volumes need to be in the same unit. So it's okay if we have milliliters or if we have liters, or if we have kPAs or mmHgs, but all of the pressure units need to match and all of the volume units need to match. So we can see a problem with our pressures. On the one hand, we have 1 atm. That's the pressure we know that it starts at, but we know at the end we're at 790 millimeters of mercury. And that's going to be a bit of a problem because those units won't cancel out. So what you need to do is choose one of them to convert into the other so that all of our pressures and volumes will be the same unit. So I can see a really easy one because I know from my notes the last time how to convert pressures. I know that 1.00 atms is actually exactly the same as 760 mmHg. If you wanted to convert the 790 mmHg, actually you'll get the same answer. Here's how we would do it. 790 mmHg, and we would say, okay, how does mmHg relate to ATMs? And I know that 1.00 ATMs, this is from my conversion factor, 1 ATM is the same as 760 mmHgs. So actually when I cancel out my mmHg, millimeters of mercury, I get 790 over 760, which my calculator says is about 1.0394, so I'll round to 1.04 ATMs. So actually I have this two ways now. I've converted this one to mmHgs, which I think is actually the easiest, 760 mmHgs, but I get the same answer if I were to convert this one to ATMs. And if I converted that one to ATMs, I would get 1.04 ATMs. So it actually doesn't matter which one you choose to convert as long as both of them are in the same unit. But going forward, I'm going to use 790 and 760 because that's just a little bit easier. So now we solve for the unknown, then plug in the values. So we know Boyle's law is P1V1 equals P2V2. And which one is it here that we are trying to figure out? When you look at the problem, it says, what will the volume be at 790 millimeters mercury? So V2 is our unknown. So how do you get V2 by itself? Of course, we're going to divide both sides by P2. And when we divide both sides by P2, the P2's cancel out. So let me clean this up a little bit. V2 equals P1V1 over P2. Now question, is it really important not to get P1 and P2 confused? And the answer is yes, that's very important. We can see from my mess here that this V1 and P1 go together. We know that my balloon was 1 liter when it was 1 ATM. So it's very important that those two numbers stay together. So let's plug those in, but remember, instead of 1 ATM, I converted that to 760 mmHgs. So let's plug in what we know already. We know that starting pressure was 760 mmHg. We know the starting volume was 1.00 liters. And we wanted to know what would happen to the pressure when it went up to 790 millimeters mercury. Now, do you see any units on the top and the bottom that can cancel out? Absolutely. We cross out the mmHgs. And so our V2 is going to be 760 divided by 790. Our new volume is 0.962. Now, what's the unit? Well, if we did our units correctly, the unit we need should be the one that's left over. Is liters a good unit for volume? Yeah, absolutely. And another really good reason to use these units, let's say I made a mistake and I forgot to convert my pressures. So let's say I used the 1.00 ATM. Can you see the problem with this? What cancels? Nothing cancels. So this is a great clue that you made a mistake if none of your units cancel, which is why we always write a unit next to every number. Only when everything cancels out like it's supposed to do we have the right unit for our answer. Okay, let's check and see if our answer made sense. Remember, we had a balloon and it was 1 liter at 1 ATM, and we've increased the pressure on that balloon. So it was 1 liter when it was 760 mmHgs. But what would happen if we pressed down on it more? What if we pressed down on it at 790 mmHgs? And we know that if the atmosphere is pushing down on the balloon more, the balloon is going to shrink. Is it going to shrink a lot if it went from 760 to 790? That's only a tiny % difference. No, it's not going to shrink a lot. It shrinks just a little. So we went from 1 liter to 0.962 liters. So you have one more question to do on your own, but I hope you have a good idea so far of what Boyle's law looks like. Remember, Boyle's law just says the pressure times the volume always gives us a constant number, which we can call K. And if we want, we can revise Boyle's law, which is the way we used it most of the time, to say the pressure times the volume at one point in time is going to equal the pressure times the volume at some other point in time. Can you remember what two things have to be constant for Boyle's law to work? It has to be constant temperature, and it has to be constant amount. So constant moles, which is the same thing as saying constant grams. So good luck with your Boyle's law calculation.